So we are getting started with the coding with Qiskit. We're going to use Qiskit. The reason we're going to use Qiskit is because that's how the paper does it to run the experiment. So I want to basically try to kind of replicate the experiments that are presented in here with real devices. Now I haven't read that, so I don't know if I do have access at all to the same machines that they have. So that's why it says here basically they've done experiments with this graph and this graph. So I'm probably better off trying with the K13, just because I think that a smaller machine will make it, and then because I won't probably have access to the other machines, I think, because they probably have some sort of agreement with IBM-Q. So let's see, conclusions. Can I gate fidelity experiments with IBM-Q devices? We evaluate our proposed algorithm by finding max cut of K13 and K14 on current processes. If the given graph is K14, our algorithm requires 5 physical qubits. Okay. 4 data, 1 ancillary, and 1 virtual qubit. Figure 13 illustrates the correspondence between the given graphs. So maybe I should do the K14, because if it's 5 qubits plus 1, I think it should be, because I think the IBM-Q experience has like a 15 qubit device available. So that should kind of work. So we're going to give it a try with the K14. Good. Let's get started. So let me see. Let's just, now it's the first time I do something that's close to these. So qiskit.org, I'm doing the live sessions with the textbook, but I haven't really, so I just need to have the documentation in handy somewhere. Get started. Documentation. So okay, cool. So I know how to install it and all that stuff. I mean, it's everything installed. So import Qiskit. I think I'd rather go with from Qiskit. Installing docs. So Qiskit. Like, can I just installing Qiskit elements? Qiskit. Okay. So we're gonna do some search if needed. From Qiskit, import everything, and I also wanted to basically get the visualizations imported. Now, how do I do that? Is there anywhere, because I forgot, is that from Qiskit visualization, import everything? I think that should be it. Let's see. Good. First things first. Let's go. So this is Grover's algorithm. So what we need to do is we're going to first need to have the oracle. So I'm going to code two separate pieces that then we'll glue together. One is the oracle, and the next one is going to be have I typed it wrong? There's a visualization. So one is going to be the oracle, and the other one is going to be the amplitude amplification, and then we'll just put the things together. So I don't know how much I'm going to get done in like about 30, 40 minutes. We'll see. So first we're going to be building the oracle. I'm not going to try to make that Jupyter notebook here anyhow pretty or beautiful, but I'll see if I can share that as well later. And I mean, if I had time, I'd just put everything in GitHub, which is probably what I will do anyway at some point. Good. So how do I get started? I would say, we'll call it, first of all, what oracle are we going to implement? We're going to follow the virtual vertex strategy, and I guess so. I guess that's what we're going to follow, right? Because then it doesn't require all these different things in here. It's all done with RZs, but again, I don't know if this is the RZ from Z rotations from Qiskit, I guess so. So we're Qiskit RZ. Can I just feel a bit lost right now? Where to start? So RZ. Searching quantum circuit RZ. Okay, that's what you've got in here. Apply RZK with angle phi to a specified qubit. With RZK, it implements a phi radian rotation of the qubit state vector, but the z-axis of the Bloch sphere. Yeah. So quantum circuit. Yeah. So I guess we'll start with a. So that happens to be for K14, right? So we could use that. And remember that what this means is that this is not needed and these control things are not needed. It's just a bunch of RZs, right? That should be enough. So if I would go and, oh, wait a second. And this was supposed to be, was this supposed to be the angle was supposed to be this, pi divided by the absolute value of E, and E was the number of edges, right? The number of edges in the graph, exactly. So this means that, so we're going to say n edges is 4 because we're doing a edges is 4 edges, right? And so the angle theta is then I need numpy. Man, I'm bad at I'm so bad at Python. I'm just so bad at Python. I'll just end up going to the Qiskit text because there's some useful examples in there. Here, Qiskit. Yeah. So this is definitely, but I wanted to have how do I was it here? From Qiskit, yeah, visualization, but I wanted to have, I want to import numpy. As NP. I'm such a noob. Import numpy as NP. Yeah. So, and it's going to be because this gives me access to pi. So this is the theta that we're looking for, right? If I print theta. So good. So this is this. Then this is the angle. Now I'm gonna have to basically. So what the oracle is, I'll say O equals quantum circuit, and we're gonna need 1, 2, 3, 4. 5 qubits. 5 qubits. How many? So I'm not gonna hear. Do I need to have how many? I guess I need 5 classical registers as well, classical qubits. So I'm not gonna play with registers right now. So this is the quantum circuit, and what I want to implement is basically so I would say what O R Z theta L on qubit 1, and I want to copy that and kind of have it for qubit 2, qubit 3, and qubit 4. Does it work? And now if I say O draw output, was it MLP? No. Just draw. No, I wanted to have the nice one. I wanted to have the nice one. No, Qiskit. MPL. Okay. So it's done that. Now, I don't know if this is. So I'm confused with the usage of the. Let's see if that works. Okay, the RZ gates here, because I keep having that problem with the RZ gates versus the Z gates. So how can I gates and instructions? Okay, gates and instructions. Parametric quantum circuits. No, gates and instructions. How can I get a list of all the available gates? Qiskit elements, development strategy, contributing to Qiskit release notes. Instruction set. What is this? And I have gates. Qiskit available gates. That's gate. So what are the available gates that I've got in Qiskit? That's the textbook. Page not found. Okay, we'll go ahead with this. Because I have the impression I shouldn't be using the RZ gates, but I should be using, is it the U1 gates? U1 theta. So apply U1 gate with angle theta to a specific qubit. So, okay, but those are equivalent up to a global phase. But it's still unclear to me whether I should be using the RZ gates or the U1 gates. That's because U1 gates. So U1 gate versus RZ gate. This is still the RZ gate, because the RZ gate, you see, and I'm looking for a 1 in here. So I'm gonna assume this is not what I want. So I'm gonna change those to U1 gates. then we can see. So I'm gonna keep it. So my intuition tells me that's what I should be. That's the direction I should be taking, because I just want to do a phase rotation on the one component. So this will be the oracle actually. Yeah, I think that's about it. So let's test this oracle for a second. So if I would make a QC, that's a quantum circuit with 5 qubits and 5 classical registers, and then I would say QC, I'm going to apply a Hadamard to the, so we're going to do this now here to the qubits 1. So the qubit 0 stays 0. Up. So this is 1, 2, 3, and 4. Okay, so if I do QC draw, I get these. Now if I do test equals QC plus oracle, and now I do test draw MPL, what? Okay, so we get the whole thing plugged together, and good. And now I wanted to basically I wanted to take a look at the how does the state vector looks like. Qiskit, visually Qiskit. So how do I, what are my visualization possibilities? So how can I visualize the plot histogram, plot Bloch vector, state CD, state Pauli vector, Q sphere. I'm looking for, I think this is these, I'm looking for plot the Q sphere representation of a quantum state here. The size of the points is proportional to the probability of the corresponding term in the state, and the color represents the phase. Okay. So here we've got an example. So we're gonna need to get a I think we don't have to measure, right? So I can just say backhand equals IR get backhand state vector simulator. And now I need to basically execute the job, right? Job equals execute the test circuit with the backhand. Then I want to get the get the result. And now I want to do plot state Q sphere business job get state vector test. Why do I need to give it all that? State vector of test. Do I need to give it the? Do I really need to give it the? Again, the circuit. Okay, what does this do? First of all, whoa. Okay, what the? How do I even read that? What the? How do I guess each point is. How do I even read that? Let's see, what else do I have? Bloch vector, no, state Q sphere, state Pauli vector, interactive visualizations, histogram, Bloch multi-vector, what is the block multi-vector of the input array using as much blocks here as this qubits are required. Oh, that's what I want. Okay, so I'm gonna do. So what do I need for that? I need just the. Okay, just these. It's iPod multi-vector, and then basically, yeah. So that's these, and now let's see what happens. Okay, so we've got here. Let's go full screen with this. Okay. So there is one qubit that's got. Yeah, but that's not gonna. That's not what I want. These are rotated. Okay. No, yeah, that's basically. So each qubit has been rotated by pi fourth. Yeah, I don't know what I expected, honestly. I don't even know what I need. I wanted to visualize. So I basically want to visualize. What do I need to visualize? How many cats there is in each possible. I want the state. I want basically my superposition. I want to see the. So state vector, state block histogram. If I plot the histogram, what do I get? Okay, just these, but I want the colors as well of the phases. I miss my circle notation. State, Hinton, credit, Hinton, cities, blocks here, histogram representation, Q sphere representation, device, circle visualizations, DAG, passment exceptions, visualizations, the iPlot histogram. So what if I do the, for this I need though probably another input get counts job. Okay, for this I need the result. That's not what I want. Cannot I see the? So what's the Pauli vector? What's that? We play with. I'm gonna be playing with all the visualizations because I don't have a job get state vector test. So why is it not working? Only support number of qubits less than 5. Come on. What other visualizations do we have? Interactive. Doesn't have to be interactive. Plot histogram, plot block vector, state CD, state Hinton, state Pauli vector, state Q-sphere, state Hinton. What is this? Plot state Hinton. What the? Okay, that's the. I don't know what is these. Multi-vector, block multi-vector. Okay, but that's the same like we did, but not interactive. That's this basically. But I'm looking for something, even like what there is in the IBM-Q. We have like the histogram with colors. I think for this I need, wait a second, I think I read this somewhere, that I need to kind of sample, like, I need to sample sample the circuit or something like that. Cascade histogram with colors, at least these blood histogram, blood embedding cascade. Blood histogram. I want to have the with face colors. I don't know if face pointed and bar colors. No, I wanted to. Damn it. So how can I see what else? The circuit visualization, interactive visualization, count and state visualizations, device, circuit. What are circuit visualizations? DAG. What are DAG? Pass manager visualizations, exceptions. Counts, interactive devices, circuit visualizations. Circuit drawer. Plot the directed acyclic graph. No. The pass manager. Gate map, circuit layout. Interactive visualizations. I want a histogram representation. I don't know how to do that. Anyway, I'll try to move on, see if the whole thing works anyhow. I'm looking for something like what you see in Quirk or what you see in the IBM Q experience, which is the histogram with the colors, right? But basically, if I go to Quirk, so, and what we're looking for is, I'm looking for something like these in here, right? So if I now do a Z of like pi divided by 4, right? That's what I'm looking for. That's kind of what I'm looking for. Because this is, so it's telling me, for example, that here we've got 2 cats, right? Because pi divided by, here we've got 0 cats, here we've got like 1 cat, here 1 cat, here 2 cats, because that's what the pi divided by 4 is doing, is for every cat, it's adding pi divided by 4 in the face. That's the whole idea. Okay. It just takes 2. Okay, so I don't know. Maybe there's a way to do that. Or I'll probably figure out later. But we've got the circuit in here. Yeah, so that seems to be. So this is what I'm getting, right? These blocks here are the ones that I see here, but that's what I'm really interested in. Okay, so back to where we were. So I've got the Oracle implemented now for K14. Now the next part is to implement. I think I'll go with the RTOF IX. I'm just curious to see how that will work out. So this is just the TOEFL part. So I'm gonna go with so another circuit that I'll. Can I not? Because that sucks that you. This is basically, I'm gonna get rid of the painting stuff. So RTOF. You can see it better like this. I like this to be basically at the top. I don't know if you can. Anyway, RTOF is a quantum circuit, and it's a quantum circuit of 5, 5. And that basically has a RTOF, basically. So what have we got? No, it's a quantum circuit of 3 qubits only. And we're going to apply a Hadamard to the qubit 2. We're going to apply a T qubit 2. We're going to apply a control knot to the qubits of 1 to 2. Now, how is the T dagger in Qiskit? TDG? I think it's TDG, right? Yeah. Artov. T dagger. Yeah. 2. So now we've got a Artov control X between 0 and 2. Artov a T a qubit 2 Artov. That's kind of like the part that feels just awkward, but I mean, you got to build a circuit at some point, right? Control X between 2. Now we're going to do the T dagger for qubit 2, and finally a Hadamard for qubit 2. Good. If we now draw, let's say, output MPL, we've got that basically. That's nice. So now there was a way you could turn that into an operation. And I think this was explained in the textbook. Qiskit. Operation, no. State vector simulator. Here. Initialize. No, this is initializing. Measure, drawing, get counts, execute. Where was that? Simplified notation. Creating custom gates, exactly. So we've got these, and okay. So now we're gonna cause Artov gate equals Artov to instruction. Okay. And so now I can simply. That's now how I should use it. Okay. So now I should go. You see, it's been actually really helpful to be playing with Qiskit before. So now I've got that implemented, the Artov IX. And the next step would be to build this whole thing in here, right? How are we going to do this? How are we going to do this? That's going to be complicated because I don't even know what qubits are connected. What am I going to connect them to and what not? So I don't know if I shouldn't first build the whole thing, run it through a simulator, and then I will basically tweak the things so they can run on actual hardware. Yeah, because now what this basically means is that I can, in order to build the whole thing now, I would need, so I've got QC is the quantum circuit, is the initial state. Then we've got the oracle, which is in test, right? Okay, but so this is QC plus the oracle. And then it's just the amplitude amplification what I need to do, which the amplitude amplification is basically, I think it's not shown in the paper, but it would be, so amplitude amplification would be, what would it be? Amplitude amplification is basically a bunch of Hadamards, a bunch of X gates. Nice. Quick. It's basically a Grover algorithm. Just can't remember those things by heart, but it's, oh yeah, so it's this thing here. It's the like a layer of Hadamard. It's a layer of X, then a control Z, which can be turned into a control X by just surrounding it by Hadamard again. Yeah. So amplitude amplification, but remember we've got here 5 qubits, correct? We've got 5 qubits. And so we need to, so amplitude amplification is going to be a quantum circuit of 5 qubits, because I'm going to turn that into an operation as well, into an instruction. So, and this is basically can I just, what happens if I do this? Draw. Can I not just apply, I must apply, can I do this? Do 0, 1, 2, 3, 4. Yeah, I can do that. Okay, cool. So this is this, then the same, but like X. Okay, and now comes that thing. So I do need to. So now I need to do something like that. Now I have ancillary qubits in between. So how many ancillary qubits do I need to cover that? So if I want to connect 5 qubits, so the first is going to go qubit 0, qubit 1, and then I need an ancillary qubit. Then the second ancillary, I think I might need 6, 7. That's going to be dirty, okay? It's going to be really dirty. So I'm going to do this, and I think I'm going to need 3 work qubits. And I think what I'm going to do now is I got to apply. I got lost. I got to apply this. So append, okay, and then I have the qubits like that. So now I got to basically do a append Artov gate, and here I indicate the qubits. So it's going to be 0, 1, right? And we're going to use the qubit 5 as the first ancillary qubit. Then the next Artov gate needs to take this 5 and do 2 and 6, right? So that's kind of the other work qubit. I think I'm gonna need more work qubits. So this takes 6 as a work qubit, and then it adds 3 and goes to 7. And I'm gonna need another work qubit. So this takes 7. Oh no, wait a second. If I do this, oh my god. Yeah, of course. But it's the only way to represent that, right? This is these, but in theory, the last one should be. Oh, sorry. So the target. I think I don't need so many, because I think if I just comment those things here out. Now, if I were to now say apply a CC naught between 2, 3, and 4, that should be fine, because from qubit 5, this is already a work qubit. Okay, yeah, that should be enough. But I cannot, I think I'll have to come back and change that if I want to really run it into a, let's do it this way. Let's just append these. Let's just do it. I'm gonna have to come back and change a lot of things. I already see that. Let's assume that works. Now I don't think I need to uncompute. So I'm sure it's not going to work in the first place. So, and it's going to be really dirty. But let's see. It's going to take a couple of videos, I guess. So now I basically do these again and these again. I should, though, before this one, I think here goes, as I said, I must apply a Hadamard in the qubit 4. And here as well, a Hadamard in the qubit 4. That's going to be ugly, yeah. But I need that because otherwise, otherwise I would. It's not a Toffoli gate. It's a control Z. So I need to sandwich it with Hadamards. Beautiful. I think, if I remember well, you can add barriers for the visualizations to look nicer. What if I do barrier? I don't know if this is just pure cosmetic. It's nicer if I draw with output equals MPL. I get this. Okay. There's something off though here. That should use the work qubit 5. The work qubit 5. Not the work qubit 2 exactly. That should use a work qubit 5 and then the other two. Yeah. Oh, but it's missing. But then I'm missing Q2 here. So I need to add. It's wrong. I need to add this one that takes in the work qubit 5 and then goes, and then basically goes to work qubit 2. And 6. Exactly. And this takes basically 6, 3, 4. That's what we need. That's what we need. Okay. Now just to explain myself, this is supposed to be this. Okay. So how can I get the drawing tools back? No. It's pity. Anyway, so this is supposed to be that part. Basically this chaining is just that the ancillary qubits the work qubits are here sort of merged in between, and I have them at the end. Q5, Q6, Q7 are work qubits, but I don't need Q7, it seems. So we've got, okay, so we've got now something here. And I think that's going to look nicer if I apply it here. So this whole thing in the middle here is basically a multi-control Z. Yeah, it's a multi-control Z. And the whole thing together, it's the amplitude amplification. Now, in theory, if I put together these pieces, and I'm going to finish the video here, so I put together these pieces and try to simulate that first. So I put together the QC, which is basically the initial part. Then I put together the oracle, which is O, and I put together amplitude amplification a couple times, and I run it on a simulator. It should give me something. It should give me these. let's see. So if I do if I now do amplitude amplification, so like this, and this should be a control. Not exactly though, because so if I move this whole thing and I apply these, this should be a superposition. So that's what you should get. Yeah, that's weird, honestly. Is this what I really want? I feel like I'm getting quite lost right now. Because no, what am I doing? So that's already in a plus state. Yeah. Yeah, but that hasn't really done anything. There's no significant. I feel stupid right now. Because that's really what is it, right? The what that circuit is. It's rotations of that angle, pi divided by 4. And then amplitude amplification. If I apply this whole thing twice, so let me see if I can take these here, these here, these here. That's just not working. I'm doing something wrong and I don't know where. Doing something wrong and I don't know where. This is amplitude amplification. Oh wait a second. Of course. I mean, I cannot ignore that. So I cannot ignore these. Maybe that's what's missing. No. What am I missing? What am I missing here? So I had a working example, but why? So this seems to be correct. It's facing the solutions that have more cats, right? By pi fourth. Maybe that's not correct. I mean, subdivided phase for the star graph K14, because basically and theta is pi divided by 4, right? E denotes the number of edges in the graph. For the cat edge determination, we introduce the following sub-oracle. Maybe I got the... Because that should work, really. What's going on here? I kind of feel like I'm missing something. This is kind of correct. So this here, pi fourth. Maybe that's the wrong parameterization. Give me a second. Any amount determined by a formula. Okay, but it's not pi. I shouldn't do this. Okay. I mean, give me a second. I think it's the way this is done is. So this, I would say here I have to go with 1/4, not pi. Yeah. Sorry, that's the problem. That's the problem. Yeah, I should have guessed that because these angles were weird. Like, yeah, of course that makes sense now. Yeah, but it still doesn't work. Okay, but now it makes sense. So here, if 0 cats, here there's 1 cat, and so it's 45 degrees for the amount of 45 degrees accumulations tell you how many cats there are. And if we put a sort of this in here and we take a look. Okay, so actually it seems like that's the solution that should have the max cat, should it? But the probabilities are really that's supposed to be the outcome, is it? I mean, how many times I need to apply amplitude amplification for this to work? What's the outcome for the K1 for the max cut? It's obviously, oh, wait a second, because see, when t is equals 4, we can get these as solutions by combining the above oracle and diffusion and repeating those the appropriate number of times. When implementing on a processor with current QV, the proposed circuit is too large in both number of qubits and depth. For example, the half adder contains a Toffler gate that requires 6. K414. So, but I kind of forgot the actual algorithm here. Initialize all qubits, flip the sign to the input where the number of edges to be cut exceeds the oracle. Amplifying the probability of, okay, the steps 1, 3. Oh, I'm stupid. You need to apply the oracle again. I'm so stupid. Okay, so this is, of course, that's at the core of Grover, my friend. I need to take this and apply the oracle again. Yeah. Okay. And so that would be max cut. So I need to apply the oracle. but the oracle is just this. The oracle is just this. So I do that here. I should pack all that into one operation. So make a gate. What do I say? Columns 2, 3, 4, 5, 6, 10. So that's AA. Yeah, that's tricky. So if I now do AA, I'm doing something off in here. Something's not right. I'm messing up. So let's clean it up in a way that I make the gates. So columns 2, 2. That's the oracle. Now I basically say clear circuit, and I get the oracle. It just feels like amplification, and so this is the initialization of the state here, right? So and now it's like we got to repeat these and that. So oracle amplitude amplification, oracle amplitude amplification. Oracle, but still it's not really. Each iteration is not really. There's no. Something's not. I think I'll have to. I mean, that's. Where am I making a mistake? So I've got all that implemented already, but like, what am I making a mistake? So that's the oracle, and the text 0, and then there's all plus plus plus. That's for K14, and that kind of makes sense, right? So clear all. So we've got like, this is our initial state, and now we're gonna do Z like 1/4 rotations for the rest in here. So, and now this kind of makes sense, right? For each. So again, the first, the last qubit is always 0 because we're ignoring this. It's always one color. The qubit that's on the rightmost here. So, yeah. And so this is the oracle. So we're going to basically make a gate and say that this is the oracle. So this is the oracle. Now, now I gotta basically apply amplitude amplification, right? Which is basically, now the question is, should I mean, the amplitude amplification here, it includes all the qubits, yeah, all the vertices. So that's basically a bunch of Hadamard's. That's basically X gates. That's another hard mark here, a next gate, another hard mark here. I'm gonna copy this, move the whole thing here, move the whole thing here, and then it's just a bunch of controls in here. So this is, in the ideal case, the amplitude. Sorry for the mic, for the big problems. This is the ideal case. Okay, and what is this? So we should execute this how many times? So we should execute these. Repeat steps 1 to 3. 1 to 3. So initialize all n qubits to plus plus plus. I think that's not. I think what you repeat is just the flip the sign of the input where the number of edges to be cut exceeds d. Exactly. Okay, so now it might be, so square root of 2 to the power of n. So so that would be square root. Can I? Like, does this work? 5 times, 6 times I should do that. But nevertheless, there's something that I'm missing here. Go away here. Should I still initialize all n cube? No, that's not. It should be steps 2 and 3. Flip the sign of the input where the number of edges, which is basically, do the oracle. Or is the oracle including the Hadamarts in here? Implementation of the oracle circuit. No, that's initialization. That's the oracle. That's just the oracle. This here is just the oracle. Okay. So this means that if I make a gate and I do 3, so that's basically amplitude amplification. You can actually get rid of these and apply amplitude amplification, right? And now I should repeat this 5 times. So 5 times. Here, 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 here. And so 1, 2, 3, 4, 5 times. And we've got these as a result. So this is the no-cat solution. And this is it's just one cat solution. That makes absolutely no... well, it makes sense because this oracle is supposed to give you the no cat, the 0, 0, 0 and 1, 1, 1 solution as a, that's kind of was the downside of it when you use this oracle. And so chances display. All the other solutions are, yeah, running out of battery. That's awesome. Okay, so that doesn't seem to work for me really well right now. Okay, I gotta figure it out somehow else. I'll leave it here. It's kind of doesn't seem like it's working, but it's because maybe of the oracles. And okay, I'll leave it here. I'll just save that. Okay, so I got all the pieces together, but it's not, when I tried it in the simulator, and I haven't really done anything with Qiskit yet here, other than just playing with constructing the different parts. It doesn't seem to still work as expected, but it's because of the oracle, maybe, right? If I replace this oracle with the one that has better results, then that should work. But We'll see. Try in the next video. Should save these though. Call Albert Market. Yeah. Anyway, thanks for watching until the end. That was a failure. That was definitely a failure.